Hello everyone, thank you for your interest in watching this demo today. I'm Mohammed and today I will demonstrate our recent work, WhiteHaul. This work was done with my collaborators Murtaza from University College London, Mahish and Peter from University of Edinburgh. The full paper is published in MobiCom this year and please feel free to take a look at it. As we speak today, there is around half of the world's population still doesn't have internet access. There are several reasons behind that, but mostly it is an economic problem. Let me explain that in more details. The majority of the population with no internet access live either in rural or low-income areas. These areas lack of affordable network infrastructure. Mainly we are talking here about the backhaul network infrastructure, where all the traditional backhaul solutions are expensive. That high cost limits the service providers and mobile operators from extending their infrastructure to these regions. To overcome the limitations and the high cost of the existing backhaul solutions, and to help enabling universal internet access, especially in the current difficult times we have, we propose WhiteHaul. The key idea is to aggregate the unused spectrum portions, usually named as white spaces, to provide a low-cost and high-capacity backhaul system. The focus of the WhiteHaul system is leveraging TV white spaces for several reasons, including the spectrum cost, the wide availability of TV white space spectrum in rural areas, and the excellent propagation characteristics which enable fewer relays and better penetration in non-line of sight conditions. So when building a TV white space backhaul system, we had different challenges that we had to address. I will not talk about the details of these challenges here, but please feel free to find them in the paper. At the end, addressing these different challenges had led us to design and implement a hybrid cross-layer aggregation system. WhiteHaul is composed of the hardware layer and a software layer. In the hardware layer, we use a multi-radio architecture. Specifically, we combine multiple commodity Wi-Fi cards using a single antenna. The RF signal generated from these Wi-Fi cards are down-up converted to TV band frequencies using a custom designed frequency conversion substrate. In the software layer, we leverage multipath TCP as a link-level tunneling technique, where we propose a new cross-layer congestion control algorithm that distribute the user traffic and enable bandwidth utilization. That combination of software and hardware layers is what represents WhiteHaul node. This is a typical deployment scenario for WhiteHaul system, where we have two WhiteHaul nodes. One is located at the edge of the rural village, and the second one is close to the internet point of presence. Before we go into the details of the demo setup, let's take a look at the setup overview. Here we have two Ubuntu 16 PCs running the WhiteHaul software layer, including the updated kernel implementation of multipath TCP with our new cross-layer congestion control. And then we have 11 AC cards at each side, so total we have 6 11 AC cards. And finally, the WhiteHaul conversion substrate at both sides. The conversion substrate consists of different components, and the detailed architecture is discussed in the paper. Let's take a look at the demo setup and then we will come back again to describe the demo steps. Here we have the setup for the WhiteHaul system. On the left hand side we have the transmitters, and on the right hand side we have the receivers. On the transmitter side we have 3 off-the-shelf 11 AC cards, where each of them is connected to Ubuntu PC through Gigabit Ethernet interface. The PC is running the WhiteHaul software layer. Let's take a closer look at each card connectivity. Each card is connected to RF mixer, which has two inputs. One is the RF signal coming from the Wi-Fi card, and the other input is the local oscillator signal coming from the SDR board. The output of the RF mixer is TV white space signal that goes directly into the combiner splitter component. Here we have the other two RF mixers, which are used by the other two Wi-Fi cards. And then we have 3 USRPs B210 used to generate the local oscillator signals to the RF mixers. We use the combiner splitter component to put multiple non-overlapping TV white space signals into a single antenna. On the receiver side, these combined signals are splitted into different ports. On the receiver side, the process is reversed, and we upconvert the TV white space signal to the Wi-Fi signal. In the first experiment, we want to demonstrate the capabilities of the WhiteHaul system by showing the maximum throughput that can be achieved. For that experiment, we will use 3 spectrum chunks, each of size 80 MHz, and with total aggregate bandwidth of 240 MHz. The following is the frequency configuration for these 3 spectrum chunks. So with the first experiment, we start with 3 Wi-Fi cards. Here we show the frequency configuration of these cards. Starting with the first card, the RF frequency is configured with 5745 MHz, and the bandwidth is 80 MHz. Then the second card is configured with frequency of 5600 MHz, and the bandwidth is again 80 MHz. And finally, the third card is configured with frequency of 5500 MHz, and the bandwidth is again 80 MHz. In the following step, we run the Python scripts used to configure the 3 USRPs. Please note that we used the USRPs to generate fine-grained and high-quality local oscillator signals for the down-up conversion process. So now we generate the TCP traffic on this link, which has a total bandwidth of 240 MHz, and we observe the throughput. Please note that both WhiteHaul nodes are running the modified version of multipath TCP Linux kernel, where we have our new cross-layer congestion control. As we can observe, the average TCP throughput is around 560 megabits per second. This average throughput represents an 80% efficiency compared to the best case scenario. In the paper, we discuss how we can increase that efficiency by increasing the inter-chunk separation. In the second experiment, we want to show the performance of the WhiteHaul system compared to the other well-known congestion control algorithm in case of packet losses. And for that, we will use the following configurations. Moving to the second experiment, and for the sake of simplicity in this demo, we use only 2 interfaces and configure their packet loss rate using Linux NetM emulation tool. Please note that the chosen packet loss rate that we configure here is based on the real-world losses and capacities observed with the actual hardware. Please find more details in the paper on how we observe these values. We start by testing the performance of QPIC congestion control, so we deploy QPIC algorithm by this system control command. And then we configure the 2 interfaces with the loss rates mentioned before. Finally, we configure the multipath TCP. Now let's generate the TCP traffic using iperf command, and let's observe the throughput. As we can observe, the average TCP throughput when using QPIC congestion control is around 64 megabits per second. And this is the aggregate throughput over the 2 interfaces. Now we will redo the experiment again, but with our new cross-layer congestion control. We do that again by system control command. Please note that we write our own implementation in TCP Illinois file in the Linux kernel. Again, here we configure the multipath TCP and then we generate the TCP traffic. As we can observe, the average TCP throughput when using the new cross-layer congestion control is around 167 megabits per second, which is around 2.5 times more than QPIC. WhiteHaul achieve almost 100% efficiency compared to the best case scenario where there is no packet losses. Please find more experiments in the paper on the performance of the new cross-layer congestion control algorithm we propose here compared to the other well-known congestion control algorithms.